However, there are methods in machine learning called unsupervised techniques. And in unsupervised techniques, you have just features and you do not have any label associated with it. For example, in case of classification, I have given you a set of labels and set of features, and then we build a model. But imagine the situation, I just give you some transactions, like in a case of fraudulent versus non-fraudulent transactions. I have given you what are the fraudulent transactions and what are their features, what are the non-fraudulent transactions and their features. However, in some case, I will just give you all the features and I will not tell you whether the particular transaction is fraudulent or not. And what I want to do is I want to basically use this feature and figure it out some pattern in these features. And that's where unsupervised learning techniques comes in handy. There are different kind of unsupervised learning techniques. And one of the most important techniques is the clustering analysis. So what is the clustering analysis? As I told you that we have a label training data where I know what is red, what is green, and I can actually work with that. But when I have an unlabeled data, where you can see here all of them are data, one color. I don't know whether they belongs to a particular kind of class. They are uniform. And if I give this kind of data, and I want to know, are there any pattern emerging out of this data? And that is where the clustering comes into play. So one way I can do is I can take this data and cluster them or group them into 4 small clusters. Okay, here I took this data actually, and I now actually put it in a 4 clusters. Here, the floor cluster is cluster number 1, cluster number 2, cluster number 3, cluster number 4. Now, these clusters I have created, whether they are good cluster, bad cluster, informative cluster, I don't know. Why 4? I can do 3, 1, or maybe 2, or maybe 5, 6. So I don't know how many clusters are there in data, first of all. And even if I can find the clusters, I do not know what is the common characteristic between these clusters. So what we want to understand in a clustering analysis is to try to see if I can actually take a set of data and create a clusters and use these clusters to do some kind of post analysis. This post analysis can be useful for different tasks. Then we can do some inference based on that and make some decisions. Remember that I started with I just set of data points with features. Then I grouped them based on some methods. And once I have these groups, I actually analyze each group and try to figure it out if there are patterns among them and if I can exploit those patterns so that I can make decisions. Let me give a simple example. Most of us do shopping, correct? All kind of shoppings. We buy clothes, we buy utensils, we buy books, we buy mobile, we buy computers, TV, fridge. Okay. Now, each time we buy something, okay, there is certain pattern emerging to it. And we subconsciously assign ourselves to certain groups of people. There is a famous example in a Western world where by doing something similar to cluster analysis, they found out that baby food or baby related items plus beer is one of the highly clustered combination. Now we find this very strange. Baby food and beer, it's mostly the beverage which is exactly opposite to the food which is taken by the particularly different segment of people. But then people actually try to analyze those people who are buying these items. They realize that one of the main feature among these customers is that they have recently become of parents. And then there's a logic behind that is following that people who become parents, they cannot go out, so they bring a beer, which is one of the leisure drink there, and drink at home. And that's why the company has started giving discount on this combo, which is very odd combo. The baby food and the beer. We get, if you buy one soap, we can two soap, we can get third soap. Correct? That's a kind of combination we get. Here you look at the combination, and this combination completely came out of analyzing the data. And this is no one can imagine this kind of combinations. So there are very surprising features sometimes we can get when we analyze these clusters, and then based on that we can make decision like the company had made decision. So that is one of the advantage of doing clustering analysis. Even if you do not have a data, you do not have a label data, you actually takes data features and try to combine those features together to create certain pattern emerging out of those data. So what is clustering analysis? The clustering analysis is try to discover similarity in the data using unsupervised learning techniques, or it is unsupervised learning techniques, which try to partition. So I have a data. Okay, I try to partition data into subset of clusters. Right? Let's say I take a uh, kind of what I call it, some kind of features for a different participant in this class, and I can actually use this to cluster uh, different students in a different categories in terms of whether they come from which state or they come from what kind of city, etc. And then there might be possible that okay, there are people in a certain colleges come from certain part of the state or certain cities alone. So my job is to take data and partition them into subset or cluster in a clustering analysis such that there is a high similarity within the cluster and low similarity across the cluster. So there is intra and inter cluster play. I have to do it. So when I have a data, let's say like this. I can create one cluster, two cluster, and three cluster. Where such manner that this set of data has a high similarity when you compare with the cluster in this particular point. However, very low cluster similarity when I compare with the point in a different clusters. The clustering analysis is one of the tool for better understanding the data. So typically, we use clustering analysis to understand is there any pattern in a data, or even visualization to get far better approaches in terms of different clusters. And we do certain pre-processing steps such as numerosity reduction, outlier removal if there is any, so that we can get a better and better clusters. As I told you, there are a lot of application for that. One application I discussed earlier was a market marketing, customer segmentation. I want to find out customers, the similarity between the customers, and target those customers and give them a customized coupons or customized promotional activities like one we discussed, baby food and beer. Topic detection in documentation, which topic it is a action drama. I can do that using clustering analysis. Information retrieval, when I want to retrieve certain information, when I search certain information, I want to retrieve certain information. If I can cluster my documents based on whether they come from, for the documents are for the cancer, or they are for the marketing, or some documents are which is cancer and marketing. So if they are in a different cluster, I can actually, if someone search for that, I can retrieve them together as a document when in a search results. Okay. Image processing, it is quite useful for segmentation. In a manufacturing, shop floor management, we want to schedule the similar jobs on the same machine, or minimize retooling, etc. You can do it with clustering. In security, anomaly detection. So there are different application of clustering analysis in different areas of the life. So what is the problem here? So if I have, let me take simple define formally. So let's say I have a data, and this is a data point x1, x2, xn, and each data has xi has some d features. Then the objective of clustering analysis is take this data and create some clusters C1, C2, let's say CM, and assign a set of data to each cluster. Some xi data are there, some xi, such that all data is at least will be in a different clusters. The data, the number of data means a number of C1. This is called cardinality. So all the clusters, summation of them is basically, so that is basically clustering analysis. So before we go, let me just define some simple definitions. So what is the centroid of a cluster? It is a mean of the data points in the cluster. So if I take j datas in a cluster Ci, then I can compute the mean, and that is nothing but a centroid of the cluster. What is the radius of the cluster? So radius is the maximum distance from a data point to the centroid. So you look at all the point and find in a Ci, all the j point in Ci cluster, and compute the distance from the mean, and the one which has a maximum distance. That is the point between that point and the mean. When you compute distance, it gives you a radius. Similarly, you can find the diameter of the cluster. So if there are different points in a cluster, then what you look for, this SQ, Q, I guess P, they are the maximum pairwise distance among all the pair in the cluster. That is called a diameter of clusters. So why I'm discussing these definitions? Because these definitions will help us to actually compute similarity between different points inside a cluster and this similarity point between different clusters. There are many clustering approaches are there. First one is a partitioning approach. And what it does, it is search all the data points and partition them into different partitions using simple metrics like means, centroid, midioid, etc. There is another clustering approach. It's called hierarchical method. What is hierarchical method is does it? It is basically try to start with all points or single points and creates a tree. So let's say this is a one you can think of. Then there will be just so this is a tree kind of structure which is there. And here we have a 1, 2, and 3 clusters. And here, each of these clusters are leaves called leaves. This is called root. There's a leaves, and the leaves has a in a simple form individual data points or sometimes cluster of data points. Then there is a density-based method. See, one of the challenge in some of the hierarchical or partitioning-based method is that if I have a shape like this, let's say my cluster is like this. Then how to actually cluster them? So density-based method use some notion of connectivity and reachability, which basically discuss how different objects are away from other objects, or different points are away from other points, and basically create the clusters. And there are very famous methods called DB-scan, optics, dense glue, which are actually density-based clustering. Then, similar to partition, there is a grid-based approaches use inherent discretization of the data point to actually create a clusters. Then there is a graph-based approaches which use graph theoretical analysis. So what is a graph? So typically we see the graph like this, correct? And then we draw something. In mathematics, there is another interesting formulation we call graph is following. So all of you, let me give an example of a social media network. All of you have a Facebook account or WhatsApp account or Instagram account. So if I take all of you, the account as a circle here, And the circles are typically called nodes. Now, let's say Facebook account. Now, we have 5 Facebook accounts, and I'm sure that you must be connected with one of that person. Some person is connected with 2 person. Some person is connected only with a 1 person, and some person will be connected with one more person. This age, this is called age. The age defines some kind of relation between nodes or 2 accounts, and this complete structure is called graph in a mathematics. So graph-based clustering approaches use this kind of graph-based theory and graph spectral theory to actually get a good clusters. And it actually can solve very interesting and complex problem, which typically is difficult to solve using other clustering techniques. There is constraint-based clustering, where users specify some certain set of clusters constraints, and then based on that we do clustering. One of them is the k-mean clustering, which is one of the simplest method to actually work, and I'm going to discuss that. And then I will quickly discuss about hierarchical clustering and some other clustering techniques in a brief manner. It is a reasonably fast method for a small data set. And often it is used to get some idea. Instead of what we can apply different clustering techniques, but K means we start with that and get some rough idea about a number of clusters are possible, or what are the patterns in the data set, so that we can apply more rigorous clustering techniques or advanced clustering techniques. And it is one of the tools which every data mining person is using. So let me discuss what is the k-mean clustering. Okay. So I have given you a set of data points here. You can see this is the data points. And what I will do is I will arbitrarily take 2 data points and assign them as a center of my cluster. And using these 2 centers and some notion of distance, I will try to find out what are the nearest point and create a cluster. So here you can see I have created cluster number 1 and cluster number 2 using this point. So these are the 6 points which are in the set C1 because they are closest to C1, this particular C1 center, and these 4 blue are in a red. Okay. Once I have this cluster, what I'll do is I will recompute their centroid using one of the definition I have actually described earlier. And let's say that now in a new C1 and C2, the centroid is this one and this one. Now what I'm going to do is I'm going to do following. I will use this new centers and now reassign the point which are closest to the different centroid. So if you look at it, if you start with that, you get this reassignment and this assignment. In other words, this particular point is actually assigned to this cluster, while this particular point is assigned to this cluster. I keep repeating this procedure until I have a convergence. It means I cannot do any more new assignment by recomputing centroid. So centroid is remaining same, points are remaining same, then I think, okay, there is no more assignment of the point possible to different clusters, so I have my cluster. So this is the very simplest k-mean clustering idea. Is this clear? Okay. So let me summarize the k-means algorithm. what you do is you choose K cluster centers first randomly, assign instance to each cluster or data point to each cluster based on the distance to the cluster centers. Centroid is one of the way we can actually compute and compute centroids of the clusters, make centroid as a cluster centers and go back and again assign different data to the cluster based on the closeness decided by the distance metric until you converge and there is no more reassignment is possible. Voila. So let me summarize what is the clustering, k-mean clustering in one slide. The problem here we are solving is following. Find k cluster centers that minimize the sum of square distance of each data point to the nearest clustering center. An algorithm is very simple. Start with the k centers, iterate until it converges. Center, once you have center, you actually go towards cluster by assigning each data point to the nearest mean. Once you stop assigning, you go back using the new cluster, you compute the center, update sample means of the data point they are responsible for, and keep doing until it converges. Very straightforward algorithm and provides you a very reasonable data, reasonable clusters. This is a more mathematically we can formally we can write the distance which we want to minimize, and finally we can we actually have what we do is we find a k-mean that minimizes all the data point and its distance between different points within the cluster. Okay. So here again, for k is equal to 2, I am giving an example. I started with this data point where gene A and gene B are there. I started with the two centers, recomputed, updated new centers, assigned data points to the new centers. Again, based on the new cluster, I have again updated, again assigned and updated. And finally, I get these two clusters. If I do k is equal to 4, what will happen? We'll see. If I do the k equal to 4, with the same procedure, I have a 4 cluster like this, this, and this. So this gives you an idea that if I change number of clusters, there will be a different clustering points. So k is one of the important hyperparameter, and finding out number of clusters is still challenging task. So one of the challenge with k-means is we may not find a global or exact clustering. We might end up with a local optima or local optimal solution. Another challenge is it can work only with the numerical data. So each of these points, I have to either have a numerical data or I have to convert to numerical data. It does not scale well to the large data set. Okay, and of course, then people try to come up with some solution like sampling other things. But as data grows, the k-means become computationally costly, and that would have an impact on your algorithm speed and ultimately clustering analysis. One of the biggest challenge here is a pre-specification of number of clusters. I have to define how many clusters I want a priori. Right? So that's another issue with the k-means. But it is the simplest algorithm, can be used by anybody, can be implemented by anybody in a straightforward manner. So someone said, okay, I can actually do something about it. I will find the number of cluster by using something called knee method, where I try to look at some metric called distortion metric, okay, and try to see how the with change in number of clusters, how much distortion is happening in my data. Okay, and here you can see that if I start with that, one is this one, two is this one, three clusters is this one, and after that the distortion is not much. It is reducing, but not significantly. And hence I will decide that okay, maybe three or four clusters are good enough. The other challenges with the k-mean clustering is how to deal with points which are on the borders of two means. So we can do is fuzzy. So with some fuzzy analysis or some with some random type, we can actually assign to one of the cluster, and that keep changing with the new update of the cluster. What we can do is another things, instead of giving a equal weight, we can give a different weight and try to adapt to width and width of the each cluster and create a ellipsoid. So instead of center all the time circle, we can also have an ellipsoid kind of by uh, giving a different weight to a different dimensions. Okay. So this is some of the choice metrics we are there. Now, in addition to this, there is also another aspect which is the quality of the cluster. I did apply k-mean clustering. I got my clusters, but how good they are? Are there any some level of analysis I can do which helps me to understand the quality of the cluster I got it? So there are different way of solving the problem. In some case, if you have a label available, then you can look at the purity and the entropy of the clusters. There is a rand analysis and index, and if there is no information on the cluster labeling, then you do use diameter, radius, Dur index, Salute score. So what is the purity? The purity is a very simple thing. You know that which cluster belongs to what. So what you find for each cluster assigned to the class that is most frequent in the cluster. So what purity is measured? By counting the number of correctly assigned the data points and divided by n. So you count that whether a given data point is assigned to the right cluster or not. So if there are k clusters and there are L classes where new I being a data point belongs to class I, then the purity will actually is defined by this particular matrix. And it looks at how many number of points are assigned to the right cluster. Of course, here I need the information of classes. I need something called labels, which sometimes is difficult to get in some of the applications. There's another concept of entropy which is used. I'll skip it for the time being. Rand index also I'll skip it, but I'll discuss Salute score. So Salute score, what it's trying to achieve is trying to achieve some kind of closeness between different points. So here, let's take a data point xj in a clusters I. Then the aj is the average distance of xj to other points in a ci. Bj is the minimum distance of xj to the each data point in ck. Okay, this is other cluster. Then the average, this average distance to the neighbor cluster is the salute in score is for the xj is b xj minus aj divided by max xj minus bxj. So if you look at the structure, you can see right away that the score can be between -1 and 1. Okay, maximum. If this is a 0, and then in that case, and xj is maximum, then it can be minus. Similarly, aj is 0, and then b will be +1. And now this score can be interpreted as following. If the score is close to -1, then it indicates that this particular data point can be better off being in a neighboring cluster rather than the cluster it is right now. And if it's a +1, then it is in a right cluster. And for each data point, if you look at this salute score, for each score, then if it's close to 1, then we have a better clustering. If it's very far from the 1, then we have a bit poor clustering. Then we have to go back and see what's happening within each cluster. Okay. So here I have given a salute score for different points. Here you can see between 0 and there are certain cluster point which is negative. Similarly, there is a Dune index. Dune index is basically computes a distance between two clusters and look at the distance within the different clusters. And the Dune index basically is a ratio of mean of distance between two clusters, distance which between two clusters, divided by max of this diameter of all the clusters. 1 second. I'm sorry, sir. I'm sorry. So where were we? So Dune index actually discusses how compact the each cluster is. So we actually compute the inter-cluster distance and take a minimum of that and look at the maximum diameter of the cluster, the height of cluster. If one cluster has a high diameter, then it brings down the quality of overall clustering. Correct? And that can be very easily figured out using the Dune index. And sometimes it also helps us to actually determine the number of clusters and etc. Okay. Now, we now have an idea about what is the purity of the cluster. We have cluster. Let me discuss another method or type of clustering method called hierarchical clustering. So hierarchical clustering is a very straightforward uh, uh, clustering techniques. What it does is following. Let me show you this particular point. We have a, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points. And what we are going to do is we are going to actually compute the distance between them using some distance matrix. And every point we are going to connect. So here we can see that these two are the connected, this nearby, then nearby. When this and this are nearby, then there is a connection between them. This and this nearby connection between them. This and this is a connection between them. So slowly, we will actually create a clusters together so that there is at the end we have a complete data. And this tree kind of structure called dendrogram. At the top, you have all the data. As you move in the tree, you will get to the individual data. And that is what is the hierarchical clustering all about. What we do is we decompose all the data objects into several levels of nested partitioning. We call it trees of the cluster. And if we with dendrogram, I discussed about it. And what we are trying to do is we are trying to actually create this dendrogram. And then we decide that, okay, I want at this level the clustering. So how many clusters we will have? At a blue level, we have a 1, 2, and 3 clusters. At a red level, I have a 1, 2, 3, and 4 clusters. At the green level, I have 1, 2, 3, 4, 5, and 6 clusters. So I can decide in a hierarchical clustering what kind of level I want to be if I can construct dendrogram using some principle of similarity between different data points. So there are two kinds of hierarchical clustering. One is agglomerative clustering, where you do not specify number of clusters, but you specify some stopping criterion. Okay. It's a computationally expensive because it does not have any number of clusters, so you keep doing it. And sometimes we use sampling methods to scale this kind of methods. Now, as I told you that we use some metric to actually define the cluster. And there are several ways of defining this intercluster distance. First one is single link. There is a complete link, average, centroid, and midioid. Single link basically look at the smallest distance between two elements in a one cluster. I mean, smallest distance between an element in a one cluster and element in another cluster. So if you have this one, and this is the point, the single link look at this distance. So this is these are set of clusters, these are set of points, and the single link look at this distance. The complete link looks at a different one. It looks at the largest distance between two elements in one cluster and another element in another cluster. The average looks at the average distance between one element in one cluster and another element in another cluster. The centroid, in case of centroid, they look at the distance between the centroid of the two clusters, and in a midioid, they will look at the midioid of the two clusters. So these are some intercluster distances which we want to use to actually create our dendrogram. So how we can do that? So if I use single link as a cluster, I can get this as a dendrogram. So I will start with, let's say, these data points. Let's say I start with this way. And then based on certain distance, I will cluster these points, these 3 points, this point, and keep doing it based on single link distance as my distance intercluster matrix. And I'll keep joining until I get a single cluster. And some point of time, I decide how much height of the tree I need. So I have decided to keep it 0.9. And there are, based on the 0.9, I have 3 clusters here. Same way, I can actually go and do the complete link where you look at the distance with the farthest point between two clusters and create this cluster, this dendrogram. and decide what is should be the height. I have decided height being 5. Again, I have a one second cluster and third cluster. Now there is an interesting point here is that I do not need to have a circle or sphere or ellipse kind of shape. I can have irregular shapes. And that's one of the advantage of hierarchical clustering, that it can leads to a irregular kind of shapes. Then I can do with average link, centroid link, and etc. Now, let me take 5 minutes and briefly discuss about density-based clustering. See, if I have this kind of irregular shapes and I want to cluster, in some cases, for example, image, I want to cluster this set of pixel together and this set of pixel together, this set of pixel together, and this set of pixel together. Now, if I want to do that, hierarchical clustering and k-means clustering would have a lot of difficulty, because how can I actually see that this point and this point, the distance, if you look at it, is very high, while this point are very, this is this point and this particular point have a lesser distance than compared to this point and this point. However, if I look at this diagram, I better make this S number of pixel as a one set of pixel or cluster than this one. And this is where the concept of connectivity and reachability comes into play, which is what is the density-based clustering method is using. They actually can handle the noise. They can discover cluster of the arbitrary shapes. Earlier, we are constraining ourselves with the sphere or at max ellipsoid. But with the density-based clustering approaches, we can actually use the concept of connected points. So we are saying that how they are connected with each other is important rather than what is the distance between them. And that is the density-based clustering. And it can actually do clustering for any arbitrary size. Okay. Hierarchical clustering, k-mean clustering can actually do this well. However, they cannot do this well. Only density-based clustering can do that, this particular clustering well. So DB-scan is one of the algorithms, which I think I will not discuss right now. But I want to show you very interesting results here. This is a DB-scan, and there are certain parameters. And you can see it can very nicely, with the optimal number of parameters, you can actually get very nice cluster back of different shapes. But you have to actually use all the parameter very in a proper manner. It is possible that you can actually lead to a poor clustering also, like here you can see even worse clustering. So DB-scan is a density-based method which helps us to do the clustering well. However, it is prone to sensitive to parameter choice. So you have to choose your parameter very clearly so that you get a nice clusters. Similarly, there is a spectral-based clustering approaches. So what I have not discussed is let me take me like this one, very simple. Think of the this kind of shape you want to handle them. Here we can have one cluster like this and the other cluster like this. This is my other cluster. How can we actually create these clusters or this and these clusters? The spectral clustering is one other method which is widely used in the literature, which help us to actually partition or cluster this kind of complex data, which is not possible with the density based or hierarchical or even k-mean clustering. Sometimes clustering can be used to detect outlier. So it can be used for pre-processing noise removal. For anomaly detection, you can use it. In those cases, the density-based clustering are widely used as a one of the tools. Numerosity reduction, if you want to do it, which basically allows you to get a tighter clusters, we can use centroid, medioid, and multiple points per cluster to do those kind of analysis. So let me just summarize the clustering analysis. The clustering analysis is the method which groups the objects or data point based on some notion of similarity, and with a wide application ranging from the image analysis, marketing, customer segmentation, to outlier detection. It uses some notion of similarity to actually uh, discretize different data types. And clustering analysis can be categorized into partition-based method, hierarchical clustering method, density-based method, grid-based method, spectral-based method, or model-based methods. And as I told you, the quality of clustering results can be evaluated based on different way. You can use Dune analysis, Dune index. You can use purity, etc. So, if you have any questions, I would happy to answer. This is what I wanted to tell you regarding unsupervised techniques called clustering analysis, which is one of the major pillar of machine learning techniques, in addition to regression and classification techniques. Do you have any questions? Any other questions on any data analysis related work? If there are no questions, then I can stop sharing. But I want you to ask questions if you have any questions. Fine, then I'll stop my presentation. I hope that I have given you good idea about what is the clustering analysis and the classification, and Professor Arun Rajkumar about regression techniques and in general AI/ML. Next, I think Indumati and Pratyay are going to teach you how to implement some of these techniques using Python. So please ask question to them also. And if you have any questions, please send an email. We will definitely reply. Little later here, but we'll reply. Okay. Thank you for your time and have a nice evening. Yeah. Thank you, everyone.